Welcome to The Explainer. Today we're diving into something that is literally mind-boggling: the extreme heavy-duty logistics required to install absolute megastructures right out in the open ocean. I mean, whether the goal is deploying these massive next-generation offshore wind turbines to power millions of homes or unlocking deep-sea resources that keep the global economy churning, the sheer scale of the engineering required to pull this off, it's just hard to even comprehend. But don't worry, we're going to map it all out for you today.
Right out of the gate, it raises a really high-stakes question. How do you build a skyscraper in the middle of a raging ocean? Because when you get down to it, that's exactly what we're talking about here. The ocean is an unpredictable, constantly moving environment. It's the ultimate antagonist. Just to give you an idea of the forces at play, ocean waves can exert thousands of tons of kinetic force per square meter. That's incredibly powerful. And engineers literally have to outsmart those raw physics just to safely deploy thousands of tons of steel.
Okay, let's dive into this mission briefing. We're taking a step-by-step journey today. First up, leaving the shore. Then, fixing the foundation. Third, installing the topsides. And finally, mastering those extreme marine risks.
All right, Section 1, leaving the shore, the birth of a giant.
So, before any of these massive engineering marvels ever touch a drop of water, their operational life actually begins on dry land, safely inside these gigantic fabrication yards. The exact sequence follows a really strict path: fabrication, transport, installation, and finally hookup. Now that might sound like a pretty straightforward, simple progression, but actually the compounding difficulty of this is intense. It's a domino effect. Every single phase must be executed flawlessly before the next one can even start. For instance, if you have a tiny miscalculation or a delay during the transport phase, well, it doesn't just mean you arrive a little late. It throws off your meticulously planned marine vessel availability and can completely derail the offshore hookup phase. We're talking delays that cost millions of dollars a single day. Once the fabrication is wrapped up, we hit what's called the load-out operation. This is where we have to physically move thousands of tons of structural components right to the waterfront. To pull this off, engineers utilize specialized skid systems and these amazing self-propelled modular transporters. They're usually called SPMTs for short, along with other just incredible heavy transport rigs. And they do this just to inch these giants down to the dock. And when I say inch, I mean literally inching them. A single SPMT can feature hundreds of independently steerable wheels. They move at this painstakingly slow walking pace, and that's absolutely crucial to ensure the load remains perfectly level and stable over the uneven ground. Let's move to and see how this builds. The primary foundational base, which the industry calls the jacket, makes its journey by being loaded onto a massive transport barge. This right here is the moment the safety net of dry land is totally removed. Depending on the specific constraints of the project, the jacket waits on the barge for either a dramatic offshore launch, where it is practically just slid right into the sea, or it undergoes a massive heavy lift. The engineering stress placed on the jacket during these maneuvers, it's immense. The steel structure has to endure extreme bending moments and shear forces that it will actually never again experience once it's permanently installed. The tension absolutely escalates as this mammoth structure leaves land behind and heads out to the open ocean. Moving right along to Section 2, fixing the foundation, anchoring the beast. So we've officially arrived at the offshore installation site. And this brilliantly illustrates a golden rule in structural deployment. You simply cannot build upwards until your base is perfectly, permanently secured. We essentially have two main engineering solutions to hold these beasts in place against those relentless ocean currents. For fixed developments, you've got the jacket structure, which gets locked in by driving huge piles right through the jacket legs, deep down into the seabed, and then that's followed by grouting. But fixed jackets usually hit their economic and physical limits at a few hundred meters of water depth. Beyond that, the sheer amount of steel required just becomes way too massive. That is where floating platforms come in. They rely instead on incredibly robust moorings and anchor arrangements to stay perfectly situated in ultra-deep waters. Now, if you're going with a floating development,
There is a staggering amount of prep work hidden beneath the waves. Floating platforms require the prior installation of moorings, anchors, flexible risers, and subsea tie-ins. All of this highly complex underwater infrastructure has to be perfectly situated and installed before the main facility even shows up at the site. And just think about the environment down there for a second. These flexible risers and tie-ins have to withstand immense deep water hydrostatic pressure, crushing cold, and relentless corrosion, all while maintaining perfect structural integrity for decades. It's a tall order.
All right, Section 3, installing the topsides, the crowning achievement. This is where the facility actually gets its brains and its operational muscle. The topsides, which is the functional upper half of the facility housing all the processing equipment and the living quarters, they are entirely separate from the foundation and are transported out to the site on their own. Engineers literally have to take thousands of tons of incredibly delicate, complex equipment and essentially drop it onto a base sticking out of the moving water. Integrated topsides are placed either as massive single heavy lifts or through these highly calculated float-over methods. Just to put the scale of those single heavy lifts into perspective, we're talking about utilizing the largest crane vessels on the entire planet. They are capable of lifting the equivalent weight of 10,000 cars, basically hoisting the entire Eiffel Tower in a single lift. The precision required for that is just unbelievable.
Now, what's really interesting about this is when a single lift just is impossible. That's when engineers use a float-over transfer. This is a precise installation method that requires very tight control of vessel motion, incredibly strict alignment tolerances, and delicate load transfer. You are literally floating the giant topside over the foundation on a specialized vessel and then carefully mating the two parts together. Doing this with millimeter accuracy while everything is floating on moving water, honestly, it's like trying to thread a needle while riding a roller coaster. It's an absolute logistical ballet, relying on perfectly timed ballast adjustments to slowly lower the topside right onto those foundation legs. But wait, once the topside is sitting on the foundation, the structure still isn't ready. We enter the offshore hookup phase. This involves critical internal lifelines, piping, electrical cabling, risers, control lines, utility connections. You have specialized teams working offshore to connect all of these systems. And look, this is way more complex than just plugging a few cables in. The hazard level during this hookup is extreme. You are meticulously integrating high-voltage electrical cabling right alongside highly pressurized resource piping, all within a hyper-corrosive salt air environment. Every single weld and connection point has to be perfectly sealed to bring this inert metal giant fully and safely to life. Finally, Section 4, mastering extreme marine risks, battling the elements. The environmental pressures pushing against this entire operation are just immense, and the margin for error out there, it's absolutely zero. Let me read this direct quote from our source material because it really hits the nail on the head. Offshore installation is, quote, highly sensitive to vessel availability, meta-weather windows, and marine operational coordination, end quote. Because the ocean completely dictates the schedule, engineers dynamically track incredibly specific meta-weather data. They're monitoring exact wave heights, wave periods, underwater current velocity, and complex wind shear profiles. It's not just about looking out for big storms. It's about finding the exact micro window where the ocean's kinetic energy drops low enough to allow a safe transfer. If you miss that window, well, the entire operation just pauses until the math lines up again. To survive out there and prevent a total disaster, engineers have an overwhelming amount of real-time monitoring requirements that they have to juggle simultaneously. Throughout the entire installation phase, they are constantly tracking ballast control, managing temporary structural support, running marine spread analysis, and keeping up with constant stability tracking. And these aren't isolated metrics. They interact with each other constantly. For example, during a structural transfer, temporary ballast control must actively and continuously counteract the immediate shifting weight of the topside in real time. If that ballast is off by just a fraction of a percent while the load transfers, Boom, that structural imbalance could lead to a totally catastrophic failure. So, the crucial point is that the ultimate goal of all this planning is to maintain stability, manage risk, and ensure flawless installation accuracy under extreme pressure. Mastering this intense logistical puzzle isn't just an engineering flex, right? It's practically a necessity for our modern world. It is the only way we're able to power vast electrical grids with deep water wind farms or extract vital global resources from previously inaccessible environments. The engineering, the coordination, the execution, it all has to be absolutely perfect to make that happen. Which brings us to a final thought to ponder today. As we continue to operate in deeper, even more hostile waters across the globe, what impossible megastructures will we have to conquer next? The ocean certainly isn't getting any calmer, but our engineering just keeps pushing the limits of what's possible. It's been absolutely incredible exploring the extremes of offshore deployment with you. Until next time, stay curious and keep exploring the structures that shape our world.
Welcome to the quiz section, Fastest Finger Edition.
Please like, share, and subscribe to Master Sense by Faraday, and turn on notifications so you don't miss new and upcoming videos.
Hey everyone, welcome to this explainer. You know, when we think about offshore energy, we instantly picture those colossal, highly visible platforms, right? The ones towering hundreds of feet above the ocean waves. And I mean, they're absolutely massive feats of human engineering. But today we're shifting our focus completely downward, straight into the abyss. We're going to examine the hyper-complex, utterly invisible subsea networks, often miles below the surface, that actually make those massive surface facilities possible in the first place. We're talking about thousands of tons of steel, robotics, and incredibly high-pressure architecture, all operating silently in the pitch black. So let's dive into this by asking a really fundamental question. What is actually required to connect a reservoir of resources located deep underground to a massive processing facility towering above the crashing waves? Well, it's definitely not as simple as just dropping a really long pipe down to the ocean floor. Not even close. We're talking about crossing a hostile threshold where temperatures hover right near freezing and the water pressure alone is enough to easily crush a military submarine. Creating a safe, reliable conduit through that kind of environment, that is literally one of the most demanding engineering challenges on the planet.
Section 1. The visible versus the invisible. To truly wrap our heads around offshore engineering, we have to recognize what's basically an iceberg effect. The absolutely crucial point here is that the massive rigs we see up top do not operate as isolated surface structures. They just don't. They are completely and utterly dependent on a closely integrated subsea system. This concealed network is doing all the heavy lifting, transporting valuable produced fluids, like crude oil and natural gas, up from those crushing depths. And simultaneously, it's pumping injection media, like highly pressurized water or gas, back down into the earth to maintain the underground reservoir pressure. Without this invisible, hard-working foundation beneath the waves, that billion-dollar surface facility is, essentially, just a really expensive floating hotel.
Moving on to Section 2, the anatomy of subsea systems.
The sheer volume of specialized infrastructure required to safely manage the flow between the seabed and the platform is just breathtaking. We are looking at a hidden industrial city down there. It starts with the subsea wells and wellheads. You can think of those as the high-pressure faucets, tapping directly into the reservoir. These are anchored into templates, which serve as the foundational footprints planted in the muddy seafloor. Then we have manifolds. Think of these as underwater traffic cops. They collect and combine the fluid flowing from multiple different wells into a single stream. Those fluids then travel through flow lines, which are basically the major horizontal highways running across the seabed. In driving this entire system are the umbilicals. These are the vital life support cords running from the surface all the way to the seabed, providing the electrical power, hydraulic fluids, and chemical injections needed to keep the whole operation running. Finally, everything funnels into the risers, acting as the main vertical elevators, pushing the resources thousands of feet straight up to the platform.
Now, when you explore subsea engineering, you're inevitably going to run into some pretty creative jargon, like pigability. I know, it sounds a little funny. It's actually named after the squealing, scraping sound the original physical cleaning devices made as they moved through the pipes. But it refers to a remarkably vital flow assurance requirement. Engineers absolutely must design these immense pipelines with the ability to be accessed and internally cleared out for long-term operation. Because think about it, if a blockage happens deep underwater and you haven't designed the system to be piggable, you are looking at a catastrophic halt in production and a massive multi-million-dollar repair bill.
And you definitely can't just buy these components off a shelf at a hardware store. The exact anatomy of this invisible city is completely dictated by intense environmental and economic pressures. Engineers have to meticulously design the interface based on the very specific underground reservoir conditions and the long-term production strategy. They have to account for the crushing water depth, the totally unique chemical properties of the fluid being extracted, those strict flow assurance requirements we just talked about, and ultimately, the specific type of platform sitting on the surface. And the margin for error here? It's practically zero. You really can't easily fix a miscalculation when it's sitting under 10,000 feet of freezing salt water. All right, Section 3, fixed versus floating platforms.
The difference between these two systems is stark, and the type of surface facility chosen radically changes the underwater engineering required. With fixed installations, the massive legs of the platform are anchored directly into the seabed. Because the structure itself doesn't move, the connection between the seabed and the platform can be comparatively direct and rigid. But floating systems, they are a completely different beast. They require highly sophisticated, incredibly flexible riser arrangements. Why? Because these systems must constantly battle the dynamic loading and shifting motions of the ocean above. The subsea architecture has to perfectly accommodate a surface facility that is heavily pitching, rolling, and heaving with hurricane-force waves, all without snapping those vital connections to the seafloor. Which brings us to Section 4, the complex execution puzzle.
Actually, physically building this dynamic underwater architecture introduces immense execution and installation complexity. It requires extreme, tightly sequenced coordination across multiple specialized departments. Imagine, if you will, handing off a highly volatile, multi-billion-dollar baton in a relay race. The drilling team goes in first to create the physical access to the reservoir. They hand off to the subsea team, who installs the foundational infrastructure and massive robotic valves. Then the flow assurance team steps in to ensure the chemical properties of the fluids will actually allow them to move through those freezing pipes. Marine experts handle the wildly complex logistics of deploying this gear from ships pitching out in the ocean. And finally, the topsides team integrates the whole shebang seamlessly with the surface facility. Just a single delay or miscalculation by any one of these teams compromises the entire architecture.
This massive, coordinated effort is entirely focused on a set of absolutely vital installation imperatives. Chief among them is mind-bending positional accuracy. Literally, imagine dropping a 1,000-ton piece of steel equipment through a mile of pitch-black, fast-moving ocean currents and needing it to land flawlessly on a target the size of a dining table. That is what they do. Once installed, they must maintain absolute pressure integrity and control system reliability in a totally unforgiving environment. And simultaneously, the interface must allow for safe, continuous host platform monitoring while ensuring we leave a viable pathway for future interventions.
And finally, Section 5, long-term operation challenges. Getting the equipment installed is a monumental feat, for sure, but surviving the depths is an ongoing battle that lasts for the entire 20 or 30-year lifespan of the well. Engineers are in a relentless, day-to-day fight against extreme operational hazards. They have to prevent hydrate formation, which are basically solid, ice-like plugs that can violently form inside the pipes due to the freezing temperatures and high pressure. They are constantly battling structural corrosion from the highly reactive seawater, monitoring the degradation of thermal insulation, and ensuring leak detection systems are perfectly calibrated. And overarching all of this is the harsh reality of intervention access limitations. You can't exactly send a mechanic down 2 miles in a submarine to tighten a loose wrench. Everything has to be heavily automated, totally over-engineered for reliability, or specifically accessible by highly specialized remote-operated vehicles.
This brings us to a really powerful conclusion from our source material. Quote, "The success of an offshore platform development depends not only on the integrity of the visible surface facility, but also on the performance of the concealed subsea network that enables continuous production from the reservoir." This perfectly captures the reality of our deep dive in this explainer today, revealing that the true, awe-inspiring marvel of these megastructures is operating entirely out of human sight.
So I want to leave you with this final thought. Next time you see a picture or a video of a towering offshore platform standing defiantly amidst the crashing waves, will you only look at the surface, or will you picture the sprawling, highly dynamic, multi-billion-dollar industrial network operating silently in the freezing abyss miles below? Thank you so much for joining this explainer. I really hope you leave with a newfound fascination for the hyper-complex, concealed subsea networks quietly powering our world. Keep learning, and I'll catch you next time.
Welcome to the quiz section, Fastest Finger Edition.
Welcome back, everyone, to another explainer. Today, we're setting the stage for a massive engineering showdown. We're heading out into the open water to explore two completely different, absolutely incredible philosophies for building giant structures in some of the harshest, most unforgiving environments on Earth. It's going to be a wild ride.
So right off the bat, here's the core mystery we really need to solve together today. How on earth do you build on the ocean floor? I mean, just think about the sheer physical power of the ocean for a second. You're dealing with crushing pressures, sudden, violent storms, corrosive saltwater, and, incredibly unpredictable currents. Trying to build anything permanent out there, it is literally the ultimate engineering problem.
Okay, let's dive into this. To actually survive these physical extremes, engineers have historically developed two fundamentally different approaches. Philosophy 1 is all about brute strength, the strategy to just stand firm using fixed platforms. Philosophy 2 takes a totally different, much more adaptable approach. That's the strategy to ride the waves using floating platforms.
Section 1. Conquering the ocean depths.
To really understand why engineers choose one philosophy over the other, our journey today is going to be a spatial one. We'll start near the safety of the shore and travel progressively out into the unpredictable deep ocean. But before we start building, let's briefly define a couple of essential engineering terms so you can clearly visualize the anatomy of these giant platforms. First, we have the jacket. The jacket is the lower framing that supports the entire structure. Think of it as the heavy steel legs of the platform. Then we have the top sides. These are the upper decks where the actual human operations take place, housing the equipment, the crew quarters, and all the active machinery. Keep these two distinct parts in mind as we move forward.
Section 2. Standing firm. Fixed platforms.
This is our very first stop on this spatial journey, where the environment is defined by shallow to moderate water depth. Now, because the water isn't insanely deep here, engineers have one massive advantage. They can actually physically reach the bottom. And because they can easily reach the seabed, they can rely on a strategy of absolute permanence.
To achieve that permanence, these platforms literally fight the ocean. The foundation concept requires a permanent connection to the seabed. Engineers transfer the incredible weight and environmental loads directly into the ocean floor using massive, deep-driven piles, or by using sheer, overwhelming gravity support. They literally make the base so incredibly heavy that the ocean just can't move it. Because of this, the construction focus is all about building incredibly robust deck framing and ensuring that the seabed load transfer happens without the whole structure buckling under the immense pressure of the waves.
Section 3. Riding waves. Floating platforms.
Let's move out and see how this builds as we travel much, much further out to sea, to a place where touching the ocean floor is simply no longer a viable option. Now we're entering deep to ultra-deep water. The depths here are, frankly, impossible to bridge with a traditional steel jacket. It would just be too much metal, way too much weight, and frankly, too much cost. So this specific environmental problem forces a radical, buoyant shift in exactly how we engineer our presence on the water.
Instead of rigid strength, we look to fluid dynamics. The foundation concept completely changes to a buoyant hull that's held in place by complex moorings or tension systems. The platform survives by essentially dancing with the marine motion, rather than resisting it entirely. Naturally, the construction focus shifts dramatically as well. It becomes all about hull fabrication, maintaining absolute stability, and calculating these intensely complex mooring configurations. And crucially, because the entire platform is actively moving with the waves, engineers require extreme riser flexibility. That means the pipes connecting the top sides to the ocean floor below must be able to bend and flex constantly without snapping. It's wild to think about.
Section 4. The engineering trade-offs.
Now we're bringing both of these philosophies together to analyze the epic logistics and the ultimate trade-offs of building in these extremes. Let's look at the installation methods. Installing a fixed platform is basically a massive, heavy-duty logistical ballet. Step 1. You bring the colossal steel jacket out and launch or lift it right down into the water. Step 2. You forcefully drive those massive piles deep into the seabed with giant hydraulic hammers. And Step 3. You bring in these massive crane vessels to carefully lift the heavy topsides perfectly onto the waiting jacket. It's entirely about grounded, stationary heavy lifting.
Now, what's really interesting here is the total contrast in the logistics. Gone is the heavy, bottom-up building. For a floating platform, Step 1 actually involves towing a massive, prefabricated floating hull out into the open ocean. It's a truly epic scale of transport. Step 2 is installing the extensive moorings into the seabed to keep it from drifting away. And Step 3 is carefully connecting those highly flexible risers and topsides while the entire structure is literally actively bobbing in the deep ocean. And this brilliantly illustrates the big picture. Here's your ultimate cheat sheet synthesizing our entire journey today. You can clearly trace the divergence directly from the data. In shallow water, you use permanent piles. You focus on seabed load transfer and you build upward. But in ultra-deep water, you rely on buoyant hulls, you focus heavily on stability and riser flexibility, and you build by towing and mooring.
So the crucial point is really about where you as an engineer choose to take on your complexity. With fixed platforms, the headache is high structural and foundation complexity. It's all about making sure the steel holds up against immense stationary stress. But with floating platforms, your massive hurdle is high marine motion and station-keeping complexity. You are constantly battling to keep a floating city relatively still in a chaotic, absolutely restless environment.
Which leaves us with a pretty profound thought about humanity's ongoing battle with the sea. Is it harder to permanently grip the seabed and fight the ocean's force head-on, or to master the marine motion of a buoyant hull floating dynamically in ultra-deep water? Think about that trade-off the next time you look out at the horizon. The ocean demands respect, and as we've seen today, engineering a way to survive it requires absolute brilliance, no matter which philosophy you choose. Thanks so much for joining me for this explainer. See you next time.
Welcome to the quiz section, Fastest Finger Edition.
Please like, share, and subscribe to Master Sense by Faraday, and turn on notifications so you don't miss new and upcoming videos. Drop a comment below and tell us what you'd like to see next.